Hello, I'm happy to see so many of you here interested in the paper DUMPLING, Fine-Grained Differential JavaScript Engine Fuzzing. To find vulnerabilities in a JavaScript engine, let's first look at a high level what happens if V8, the JavaScript engine running in all Chrome-based browser, executes a snippet of JavaScript. This snippet of JavaScript may be passed back and forth through these four so-called execution tiers. There is Ignition, the interpreter, as well as Sparkplug, Marklev, and Turbofan, which are just-in-time JIT compilers which differ in the amount of speculation they apply and optimizations they do. The interesting observation from a security point of view is that all these execution tiers must execute JavaScript semantics in the exact same way, to the point where even if Ignition interprets, has a return value, have the value minus 0.0, and Turbofan does some optimization where the same return value has the different float value plus 0.0, this can be enough to gain remote code execution in the renderer process. So knowing this, we think it's important to have a better automatic way to find such differentials. A key data structure we use in our approach is the virtual machine state. After JavaScript gets to the JavaScript engine, it is first translated into a register-based bytecode representation. And at any point in the program, at any program counter, you can have, there exists a VM state, which is just a collection of all the registers, as well as the program counter itself, a copy of global context, and so on. The important property of the VM state is that it's enough to resume correct JavaScript execution at any point in time. At first, this bytecode representation will be interpreted, but JavaScript engines want to go fast. So a function that is frequently called with the same types and ranges will eventually be JIT compiled through various optimization stages and intermediate representations, which all could have bugs, down to the machine code for the native architecture. Our idea in the paper is now to run the same program twice. Once with optimizations disabled on the left, and once with all the optimizing JIT compilers enabled on the right, and compare these VM states I just showed you at a high frequency to detect such differentials. So, as I said, we collect the traces, even from JIT, where it's non-obvious how to collect them, but I will get to that soon. Then we match them together, and with these first two ingredients, we get a differential bug oracle that we can plug into a state-of-the-art JavaScript engine fuzzer like Fuzzly, and to generate interesting JavaScript samples at a high scale. And in our evaluation, we find 8 new bugs in the already well-tested and also differentially fuzzed V8 JavaScript engine. Let's talk about how we do the state extraction. Especially from JIT, where the state is spread across registers and the stack. So there are two obvious questions. How do we get back the state from machine code? And where even is the state extraction possible? Also, we set ourselves the constraints of we don't want to influence JavaScript execution semantics in any way. Especially, we do not want to change the input program and instrument the program in input space. We also don't want to change any JIT compiler optimization, as we want to find bugs in them. What we use for this is our de-optimization points. These are present in all speculative JIT compilers, especially also all JavaScript engines in all modern browsers. Let's look at function f. It takes O1 and O2 as inputs, and after it's executed lots of times with the same types and ranges, it will be JIT compiled with some assumptions made. For example, that O1 is an object and not a primitive type, because at some future point, the engine can't be sure that f is not called with a 1 being an integer or something. So right before a 1 is used in the execution, the JavaScript engine inserts a so-called de-optimization point, which just checks, I highlighted it here, is a 1 an object? And if a 1 is not an object, the JIT compiler holds enough context such that it can de-optimize back to unoptimized execution. De-optimization means restoring the VM state and continuing execution, for example, in the interpreter at this exact bytecode instruction, or maybe 1 or 2 or 3 bytecode instructions back. So basically, the optimization points are what we need. It is a mechanism already in the engine that allows us to get the VM state back during JIT execution. So how do we use these de-optimization points? After each de-optimization point, we just add one more assembly instruction, which is a call to our dumpling hook, which saves the state, the machine state on registers and things, and then does what de-optimization would have done, meaning restoring the VM state, rematerializing escaped values and such, and then we dump the VM state, hence the name, meaning we just add the state to our trace or thing printed out or something, right? Then we jump back to where we called the hook from, after restoring the state from step 1. So in summary, we do make partial use of this existing de-opt mechanism to get the VM states back while we're in JIT execution. The cool thing about it, it's totally transparent to the execution. We didn't change any optimizations. The JIT is not affected at all. We do the same then during interpreter execution. After doing the optimized execution, we know to what bytecode offset there are de-optimization points pointing to, and then we can just get the VM state, which is a C++ object from there, and both in unoptimized and optimized execution tiers, we call the same VM state serialization function, which we wrote to be invariant across engines, so we don't have any C++ heap addresses in there, but other than that, it's basically what a debug print would have given you, and it's fine-grained, so you can see, for example, we see the difference between infinity and minus infinity, and we go deep into the objects to capture all the detail of the VM state. In practice, it's a bit more compressed, but here for readability. Then we need to compare the two execution traces. Unfortunately, in the interest of time, I can't go into too much detail on how we do this. Just 2 quick points. There is no one-to-one mapping of dumps. It's basically because we can go 1 or 2 or 3 bytecode instructions back. But the observation that the VM state is the complete state of the program, and we can't have any duplicates of VM state, otherwise we would have been in an infinite loop, and the observation that obviously our fuzz case terminated and wasn't in an infinite loop, brings us to the conclusion that we can just check if all the JIT dumps are in the set of interpreter dumps. Obviously, all this dumping, these frequent partial de-optimizations have an overhead, but we're pleased to see that even with this very fine-grained, exact bug oracle, we're still competitive when it comes to coverage over time and execution speed with other differential fuzzes and non-differential fuzzes, the state of the art here. We're happy to find 8 new bugs in the V8 engine and get some bug bounty offered by Google. Interestingly, we find both bugs in the JIT engine as well as the interpreter. I want to show you one of the bugs we found. This is basically what the fuzzer generated. The details of this bug don't matter too much, but with this sample, Dumpling is already able to catch the bug that the engine does some wrong optimization, or the interpreter is wrong, which actually in this case was. But there is nothing visible to the user of this program at this point, right? And certainly not to other fuzzers, which the state of the art basically relies on some version of adding a console log. So you would need to query this broken state and to observe that with optimizations enabled, this is true, and with optimizations disabled, this is false. To conclude, the key problem we wanted to solve with Dumpling is finding differentials between JS engine execution tiers automatically. And with Dumpling, we managed to do this by extracting VM states during runtime at a high frequency from both JIT and interpreter, and having an algorithm to compare them. We leverage a mechanism already in the JS engine, and not just a mechanism present in V8, but other JS engines also have this mechanism, to implement our bug oracle. And as a result, we can find bugs before they become so-called visible, you could say. Thank you for your attention. Our artifact is available at this link. Feel free to get in contact with me at these socials or here in person at the conference. I'm now happy to take any of your questions. Thank you.
Thank you. Any question?
A very interesting talk. Can you tell us a bit more about the differential oracle? I'm interested how complicated it is to match the state across engines. Did you try that? Is it like more complicated than in the same engine across optimizations?
Well, our paper is already only about V8, and we specifically didn't want to do cross-engine testing because it is interesting to find differentials across engines, but these are not necessarily security bugs. They're basically an wrong implementation of the spec, or like one engine implemented the spec wrong. There are other works that are basically doing the equivalent of console log to test across engines. You can implement the same thing to work in other engines, SpiderMonkey or JavaScript core, but I don't think it would be very viable to use the dumpling approach to test between engines, because the details of the VM state might be different.
Okay, yeah, thanks.
Another question? Okay, so we'll stop here. Thanks again.
Thank you.